strict inequality, and again for the losers, we have a weak inequality, and we assume that at least one of them is strict, and this problem disappears. Now again, this is very, very simple and straightforward. The question is, by making this modification, do we open ourselves up to any other problems? And the answer is, well, perhaps. But in order to answer that question, we have to look at the properties of this notion of Condorcet dominance. And basically, one way of looking at this is to look at properties of collective choice rules or voting rules and see whether they could possibly generate a conflict. And for now, I'm just going to look at two properties that we think are fairly plausible in this context, and we compare them. We compare the performance of our criterion with alternatives, particularly one that's been around in the literature for some time, that's developed by Smith. Smith has an alternative, a weakening of strong Condorcet consistency by applying it to sets rather than to just to singles. Basically, the subset of the feasible set is what he calls a Smith set. If everybody in this subset beats everybody who is not in the subset, according to, in a pairwise comparison according to the majority rule, right? Let me just write this down. So a set, a non-empty set T, which is a strict subset of a feasible set S, is a Smith set for profile R in the feasible set S. If, again, the strict variant of this inequality is valid, and now for all x in this subset, and for all y in the complement. Right? Clearly, a special case of this is if T is a singleton, we get back the strong Condorcet winner. But this is a set-based generalization of Condorcet, of the notion of a Condorcet winner and a Condorcet loser. Notice I didn't specify winners or losers in that set, because one observation is that once we write down a restriction based or a consistency condition based on the Smith set, the distinction between the two disappears, because if you're in the Smith set, you're a winner. If you're not in the Smith set, you're a loser. So in that sense, if you have a consistency condition that says pick something from a Smith set, it automatically implies that you cannot pick anything from the complement. So there is no different notions of winner consistency and loser consistency. It boils down to a single property. And that may in itself be considered something that could lead to problems, and we'll get to that shortly. So basically, what we call Smith consistency, basically it says if you have a Smith set, then choose only from that Smith set and choose nothing from everywhere else. There's one potential complication, but it isn't really, and that is that Smith sets need not be unique. And again, you can easily see why this is the case. Suppose we have a situation where there are only three alternatives, X, Y, and Z, and suppose our profile is such that everybody prefers X to Y and Y to Z. Translate. Well, there are two possible Smith sets. One is the singleton X, and one is the set XY. They're both Smith sets, right? Because they have the property that everybody in the set beats everybody outside the set. But clearly there's a noticeable difference between the two. Given the presence of X, it seems rather unattractive to include Y. And then we can always do that because if there are multiple Smith sets, they'll always be nested. And then you can see why this is the case, right? Suppose we have two Smith sets, T and T prime. And suppose they're not nested. Well, what happens? Here's our feasible set S. Here's the Smith set T. Here's the Smith set T prime. Suppose there are elements in T that are not in T prime. Say X. Well, suppose there are elements in T prime that are not in T. Well, that can't be because T is a Smith set, this has to beat this, and because T prime is a Smith set, this has to beat this. Therefore, even if there are multiple ones, there will always be a minimal one because everything is finite. So we can phrase everything in terms of models. I'm sure we didn't discover this. This was open. But so basically, Smith consistency now says never choose anything that's not in a Smith set, or you could say only choose objects that are in all Smith sets, or equivalently, only choose objects that are in a minimal Smith set. So if there is at least one Smith set, there is a minimal Smith set, and that's the one we choose. So if there is, again, pick any profile with a feasible set. If there exists a minimal Smith set, which means there must be a minimal Smith set because it's nested, then the same criterion applies. The set of selected objects should be contained in the minimal Smith set. In the minimal set of Smith winners, let's call it. So this is the minimal set of Smith winners. Then that's the elements in the smallest. Okay, now to compare these two, we're looking at two properties. One of them is an intra-profile condition, and we think it's fairly essential. It basically says don't choose dominated alternatives, or don't recommend dominated alternatives. That seems quite a fairly innocent requirement, innocuous requirement to us. By dominated, we now mean that if there is, suppose there is a candidate X, and suppose there is another candidate Z, such that Z beats X according to each individual voter's profile, preference, then it would be difficult to argue that X should be considered to be in a privileged position. So if you formulate this as the exclusion of dominated candidates, basically what you want is, if you look at any situation with a profile with a feasible set S and any feasible candidate X, if there exists another alternative Y that's feasible, distinct from X, such that Y is strictly preferred to X, not only according to a majority, but by everyone, then we can reasonably assume or require that X should not be chosen. Now it turns out this is not a problem for intermediate Condorcet winners, because if you're an intermediate Condorcet winner, this can never happen, because you beat everybody. Right? You beat or tie with everyone else, so it's never possible that you could be dominated. Right? This is clearly a property that cannot generate a conflict with intermediate winner consistency. But it can create a conflict with Smith. And again, it's easy to find an example. Well, easy, exposed everything's easy, but it's possible to find a quite simple example, I should say. Suppose we have one universal set and a feasible set S that has 4 elements. So I said W. And suppose we have 2 voters, that's enough. And our preferences are such that voter 1 has Z better than X, greater than y greater than w. And voter 2. Voter 2's preference is y better than z, better than x better than w. Now, does this profile and this feasible set have a Smith set? The answer is yes. There is only one of them, and that's the set that consists of x, y, and z, because all of them beat w by a score of 2 to 0. Is there another smaller Smith set? The answer is no, because if you look at x certainly doesn't beat anyone else other than w by a majority. Y doesn't, because there's a tie between y and z. And z doesn't, because for the same reason, because there's a tie. So the only Smith set, therefore the minimal Smith set in this set is x, y, and z. But that's bad news because x is w, right? So the Smith set, Smith principle